Rightio, let's have a look at crystallization and what solubility means in terms of forming crystals of compounds. Okay, so we talked about how when we have a supersaturated solution, we can seed crystallization really easily and it's unstable and we'll start to see crystals. So let's have a look at that and why we're interested in crystallization. This is related to chapter 14.2 from your textbook. So crystallization is where we start to see crystals or solids form in a solution. Generally, these are ionic, and remembering that ionic compounds have a crystalline lattice, so they will form crystalline solids. And what we can do is we can form crystals in a solution in two ways, or from a solution in two ways. One is to cool a saturated solution, remembering that a saturated solution contains the maximum amount of solute at a specific temperature, and that solubility generally increases with temperature. So if we cool the temperature, what we now do is reduce the amount of solute that can be held by that solution. And as a result, we start to see crystals form. The solid coming out of solution, and as it does so, depending on how quickly it does this, the crystals will appear to grow slowly or very, very quickly, and that will determine the size of the crystals. Okay, so by lowering the temperature, the solubility of the solute is reduced, and we start to see that extra solute coming out of solution in the form of crystals. Okay, so remembering that the crystallization temperature we defined in our last video as the temperature where crystals start to form. Okay, so that's the point where we'll start to see crystallization happening. The other way we can do this is evaporating the solvent from a solution. And this is the way that we actually farm lithium crystals or salt in various countries. So this is used for mineral salts, where they flood terraces with water and then allow the sun to slowly evaporate the water, leaving behind crystals. They use this process for farming lithium salts, which are then turned into your lithium hydride batteries, which power, or lithium ion batteries that power your phone and your laptop. It's also used in some places for forming rock salt or sea salt in places where it's not actually mined because it's formed in large veins. Okay, I'm going to play you a video which shows crystals forming in solution. What we're actually going to see with this is a number of different crystals forming from solution, and we can see that they have this regular geometric structure, which is a result of that ionic lattice, okay, giving it a regular geometric pattern. So have a look at these. Some of these are quite interesting in the shapes that the crystals form. See that the crystals slowly appear to grow as the solid starts to fall out of solution. And depending on the compound that the crystal is made from, it changes the color or the shape. Okay, so this is sodium ethanoate, which forms is one of the ones that will form a supersaturated solution. So as we saw in that video, crystals can form at different speeds. Some of those were sped up to 1,000 times, sometimes were at 1-to-1 speed and relative speed. And the speed with which the crystal forms can actually change its shape, how regular the shape is, and the size of crystals that we see. This picture here is actually of a large copper sulfate crystal that has been grown slowly over time. And you can see this is actually in a 200 ml beaker, so this crystal is quite large. And I'll show you one of these in class the next time we're in class so you can have a look. And when you look at this, you can see the regular shape and regular pattern that is determined by the structure of the lattice for the ionic compound. So this one here, these are not compound crystals, these are actually ice crystals, these ones. And there's a fabulous book that was the product of a person's research that looked at the different temperature effects in our atmosphere that change the way in which water crystals grow. And by changing the level of humidity and the temperature, these snowflakes show different patterns. So this is one way that we can see that we can influence the way in which crystals grow by changing the conditions under which they grow. And for chemical compounds in the lab, crystal size and shape are what are affected. Okay, so we can change the rate of evaporation by the solvent. Okay, so the faster we remove the solvent, i.e. the warmer we heat something up to drive that solvent off, then the smaller the crystals that we see form, because those crystals are going to form much more quickly. We can also do nucleation. This is where we provide a seed crystal, so usually a crystal of the compound we want to crystallize, that the crystals then will grow around that seed crystal, like layers around an onion. Okay, so the crystals are built up layer by layer, and the crystals seed onto this or grow onto this. So we have a seed crystal. The other thing is we can sometimes use a glass rod on the bottom of the beaker to create a rough surface that causes the crystals to seed onto, or even a speck of dust. This is the role that the metal disc plays in those hand warmers. When the metal disc snaps, it creates an unevenness which seeds the crystallization in our hand warmers. The other thing is the nature of the compound. The shape of the crystal is dependent on the type of compound, and that's dependent on the lattice that we see, okay, that ionic lattice. So these things affect the shape of the crystal. The rate of evaporation of the solvent affects the crystal growth, and how saturated. The other thing that we can do is how quickly the evaporation of the solvent. So if we start with an unsaturated solution and let this solvent come down very, very slowly, we can start to see large crystals, because eventually it will become saturated, and then from saturated it will start to crystallize. So when we look at crystallization, we go back to our solubility tables, our solubility curves, and we can predict how much crystallization we would expect to see by changing the temperature, and at what temperature we would expect to see crystals start to form. Okay, so if you have a look at this one here, we're told that 50 grams of potassium nitrate is dissolved into 100 grams of water at 40 degrees C. So you would go back and look at the solubility curve, okay, that we looked at in our previous video, but is also in your textbook. And the question asks us, what mass of potassium nitrate crystals will form if the temperature is reduced to 20 degrees C? It's telling us to go back and look at the solubility curve. What you are going to do is determine the solubility at 40 degrees C, okay? And that will be the mass of solute dissolved in the original solution. Okay, so 50 grams of potassium nitrate is dissolved in 100 grams of water at 40 degrees C. You're going to find that on the solubility curve. It may be unsaturated, it may be saturated, but you're going to find that on your solubility curve. Then we're reducing the temperature to 20 degrees C. Okay, so we've got our solubility curve. We're at 40 and we may be here. At 20 degrees, we need to work out what the maximum amount is at that temperature. So we use our solubility curve, and if you look at this one, okay, we would find that the maximum that would dissolve is 32 grams. Because we put in 50 grams initially, we had 50 grams dissolved into the solvent. We've now decreased the temperature to where only 32 grams can stay. Okay, 32 grams stays in, so therefore the initial amount we put in as 50 minus the 32 that stays in solution will mean that 18 grams of potassium nitrate will be seen to crystallize out at 20 degrees C. Okay, because the maximum that can stay in solution is 32 grams. We put in 50 at the warmer temperature, so as the temperature cooled, we will start to see crystals of potassium nitrate form in our solution. Okay, to have a go at practicing one of these yourself, try it yourself from your worked example in your textbook. So just a point on gases and solubilities. When we talked about the fact that solubility tends to increase, okay, with temperature, this is the solubility of ionic solids or solids, okay? Increases with temperature. And that makes sense if you think about it, because an aqueous solution has a higher kinetic energy than a solid. So in order to get enough kinetic energy for the particles to be floating around in solution, we need to add energy in. So if we add energy into that system, we will get more kinetic energy, we will get more solid dissolved into the solution. However, that's not the case with gases. Unlike solid substances, the solubility of gases decreases. Gases already have a high amount of energy. So if you add temperature to that, the gas is going to try and escape from solution. It's going to have more energy. And you've seen this if you happen to leave a bottle of soft drink out in the sun. And when you pick it up, it feels really tight. Okay, because the gas has started to come out of solution. And then if you open it, all the gas will escape and your Coke or soft drink would be flat. Okay, and this is because as the temperature increases, the solubility of gases, okay, solubility of gases decreases. Okay, and this is what we see. So you may have heard of methane ice. Okay, where we're getting methane bubbles coming up from ice with rising temperatures of our environment. Okay, so this is methane from deep, dark lakes that are very deep, where methane is bubbling up to the surface and getting trapped in ice as it starts to come up. Okay, so gas solubility decreases as temperature increases. It is the solubility of solids that increases with increasing temperature. Liquids, when two liquids dissolve into each other, we refer to it as miscibility. This doesn't change with temperature. That is based more on the polarity of the two liquids, okay, whether or not they're miscible, and that doesn't tend to be influenced by, it doesn't follow trends in terms of increasing miscibility or not with temperature. So just going to leave you with this and our discussions on solubility, and have you think about what that change in gas solubility means for our environment and how that might impact aquatic ecosystems in the future as we see rising temperatures on our planet. These are the key questions for you to complete. This would complete 14.2. Remember to include key definitions. You need to know each of your types of saturated versus unsaturated and supersaturated solutions, crystallization temperature, and those new terms that we addressed. And I'll see you in class.